So limit at infinity. So let's look at the difference between infinite limits and limit at infinity. Infinite limits are the following. We saw that earlier in the semester. It's the limit of f of x when x goes to x approaches a, when the limit equals infinity, or the limit when x approaches a, the limit itself equals negative infinity. Those are infinite limits. In other words, the limit itself goes to either infinity or negative infinity. Okay? Normally these limits represent a vertical asymptote. And we discussed those earlier. Okay, what about limit at infinity? Well, the difference is the following. Those will be the limit that behave like this, the limit of f of x when x approaches infinity equals L, or the limit of f of x when x approaches negative infinity equals L. Okay? And so those are what we define limit at infinity as x goes to plus or minus infinity. So that's the meaning of at infinity. And this limit represents a horizontal asymptote. I think I have spelling issue here. Okay, here's a quick example. For instance, we want to analyze the function f of x equals x squared minus 1 over x squared plus 1. Okay, so, and then there is another part, then evaluate the limit as x approaches plus or minus infinity of f of x. Okay, so we have two parts. We have the analysis part that we need to perform first, and then we need to evaluate. When we analyze rational functions, there are certain things that we need to look, and if you go back to your pre-calculus days, remember, you learn that you need to look at long-term behavior and short-term behavior, right, of a function. That's what the meaning of analysis. And then, as part of the short-term behavior, we looked at the zeros of the function. We look at the y-intercept if there is one, and we look at vertical asymptote. When we look at long-term behavior, we looked at the horizontal asymptote, or if there is no horizontal asymptote, maybe we have an oblique asymptote, and or maybe we have infinite limits. Okay, or limit at infinity. Long-term behavior, we're talking about the limit when x goes to plus or minus infinity. So let's write as far as analysis is concerned. Okay. So we're looking first short-term behavior. In this part, we're going to look at the zeros or the roots of the functions. In other words, root or x-intercept, which is all synonym. We're going to look at y-intercept. And if there is a vertical asymptote, it will happen for short-term behavior, small value of x. Okay, when we're looking at long-term behavior, what we're looking at, we're looking at horizontal asymptote, and those are, we're looking at oblique asymptote or slant asymptote if they are, or essentially we are looking at limit at infinity. Okay, basically it's or. In a way, there is a measure of redundancy right here. So let's look, according to these highlights of the analysis, let's see how example fare. And here's the page I was looking for, page 1 of this of the notes for this class. So let's apply our function. Let's keep it like, let me do this, let me put it side by side. Okay, so let's look at short term. So f of x equals x squared minus 1 over x squared plus 1. So we first check out the short term. And the first thing on the list was the zeros. So we want to find out for what value x squared minus 1 equals 0. It turned out here we're going to end up having x equals plus or minus 1. Okay, so we have 1, 0 at x equals negative 1, and the other at x equals positive 1. So, like so. What about the y-intercept? We want x to equal 0 and f of y equal f of 0. So we look at negative 1. Let's do it this way. 0 minus 1 over 0 plus 1. So we're looking at negative 1. So y-intercept will be 0 and negative 1. Okay. What about vertical asymptote? For vertical asymptote, basically we're looking at what? We are looking for the denominator to equal 0. But since x squared plus 1, x squared plus 1 can never equal 0, then we end up having no vertical asymptote. Okay. So we found out the zeros, the y-intercept, and we found out there are no vertical asymptote for this function. Okay, now we need to turn into long-term behavior. In the long-term behavior, we want to find out what is the how the function look like. And you recall from, again, pre-calculus that the limit of the function can be approximated by ratio of the limit of the leading terms. So you know from pre-calculus that the long-term behavior of the function would be y is approximated by ratio of leading terms. And the leading terms, if x squared minus 1 and x squared plus 1 are a polynomial respectively, then we are looking at x squared plus 1 divided by x squared plus 1, so it's 1. This tells you that the limit y equals 1, remember y equals 1 is probably the limit at infinity, the limit when x goes to positive or negative infinity. Okay, so by this we can say that the limit of f of x as x approaches plus or minus infinity probably going to be something like 1. Okay, so now we can sketch the function. And let's see what we learned. We learned that this function has zeros at 1 and negative 1, right? Has y-intercept at negative 1. So these 3 points right there, x equals negative 1, y equals negative 1, and 1 are 3 points where the function is going through. Plus, we know that the long-term behavior is for large values of either positive or negative x, it approaches 1. So if this is y equals 1, the asymptote, the horizontal asymptote, probably going to be right here, y equals 1. So we know that the function going to come from the left or from the right, from the bottom part, will go like so. We'll have to pass through 1 and 0. We'll have to pass through 0 and negative 1. We'll have to pass through negative 1 and 0, and like so. So this is how the function is going to look like. Okay? And we can see from here, so the limit, to evaluate the limit, we can say that the limit of x squared minus 1 over x squared plus 1, when x approaches plus or minus infinity, will be 1 from the behavior of this function. Okay?